Next up is isocitrate dehydrogenase. So now we know we've got isocitrate formed, and it was formed. Why was it formed specifically again? Because it's a secondary alcohol, and so it can be oxidized in this next reaction, which is the isocitrate dehydrogenase reaction, which is an oxidative decarboxylation reaction. So two things are happening. And we can see we go from isocitrate to alpha-ketoglutarate via isocitrate dehydrogenase, which is the enzyme. So it happens in two steps. The first step is the oxidation itself, where NADH is produced. So NAD plus is reduced to NADH when isocitrate is oxidized. And then the second step is the decarboxylation, where this carbon and two oxygens is removed as carbon dioxide. This intermediate is very unstable, and it is the decarboxylation step is highly favorable. So this isocitrate dehydrogenase reaction is the first reaction that is going to link the citric acid cycle with the electron transport chain and oxidative phosphorylation. Why? Because of this. It produces the NADH, which is going to be used in the electron transport chain, as we shall see, to generate energy via ATP. Now, as we saw when we looked at the spontaneity of this reaction, we saw it had a large negative free energy of hydrolysis, and hence it is a regulated reaction, the isocitrate dehydrogenase reaction, and NADH and ATP, both being products of the citric acid cycle, are allosteric inhibitors of isocitrate dehydrogenase, meaning that when the citric acid cycle is producing too much NADH and ATP, it makes the cycle slow down by inhibiting this enzyme and making less alpha-ketoglutarate go into the cycle. ADP, on the other hand, is an allosteric activator. So when your ADP to ATP ratio is high, meaning you do not have much energy and you've got too much ADP, it actually activates isocitrate dehydrogenase and allows the reaction to happen. And in fact, the reaction won't happen in the absence of ADP. It requires ADP to activate the reaction. Okay. So the next step is the alpha-ketoglutarate dehydrogenase reaction, which we said is also an oxidative decarboxylation reaction, just the same as the one before. But the difference is that this reaction, we said, happened in two steps: first oxidation and then decarboxylation, and that is because isocitrate dehydrogenase is just a single enzyme. But in this reaction, this alpha-ketoglutarate dehydrogenase is actually a multi-enzyme complex. So this oxidative decarboxylation happens within the complex. So we don't see the intermediates, and we go directly from alpha-ketoglutarate to succinyl-CoA. And just like with the pyruvate dehydrogenase complex, where there were a number of coenzymes involved, similarly alpha-ketoglutarate dehydrogenase also has coenzymes involved. And there we see the use of coenzyme A here to produce succinyl-CoA. Okay, so it's a multi-enzyme complex, and so it appears to occur in a single step, and we do not see any intermediates. NADH, carbon dioxide, and succinyl-CoA are the products. So it is oxidative decarboxylation. So this group here from alpha-ketoglutarate is removed as carbon dioxide, and NADH is produced as well because it is a reduction reaction. NADH and succinyl-CoA are both energy-rich products which can be used in subsequent reactions. The next reaction, Sassenal-CoA synthetase reaction. So we said there are two high energy molecules that were produced. What were they again? We said there was NADH, and NADH we know is high energy. It will go off to the electron transport chain to make ATPs, as we shall see. The other molecule is Sassenal-CoA. Now, why is Sassenal-CoA a high energy molecule? Remember, it is connected to coenzyme A. And how is succinate connected to coenzyme A? Via what bond? It's a thioester bond. And we said those thioester bonds are high in energy. So, because Sassenal-CoA is a high energy molecule, it is able to drive substrate level phosphorylation. Remember, ATP can also drive substrate level phosphorylation reactions due to the fact that it has got high energy in the phosphodiester bond of ATP. Similarly, the thioester bond of Sassenal-CoA also contains high energy. And so it will drive substrate level phosphorylation of GDP to produce GTP. So there's Sassenal-CoA via Sassenal-CoA synthetase produces succinate, and in this way GTP is produced. So it's quite easy to know the structures of all these metabolites in the TCA cycle. Remember, I said you would need to know the structures of the metabolites in glycolysis and the TCA cycle. Those are the only structures that you would need to know, but it's simple to see how one structure goes from one to the next. You know when there are oxidative decarboxylation reactions, you know how many carbons should be present from the beginning and as we go through the cycle. So here we can see that we now only have 4 carbons from this point onwards to the end, to the creation of oxaloacetate. There are always 4 carbons. So we said the energy is contained in the thioester bond. Then, in a side reaction, GTP can be converted to ATP by the enzyme nucleoside diphosphate kinase. So once that GTP is formed, it can be converted to ATP. And of course, ATP can go on to the electron transport chain. Well, it doesn't have to, it's already there. Next reaction, succinate dehydrogenase reaction. Now, succinate dehydrogenase is the only enzyme in the citric acid cycle that is not a soluble enzyme. It is in fact a membrane-bound enzyme, and interestingly enough, also has a completely other function. Well, it is related, but it forms a very big role in the electron transport chain as well, where it's got a different name, succinate coenzyme Q reductase, as we will see. So succinate dehydrogenase, succinate coenzyme Q reductase are the same enzyme. Succinate dehydrogenase participates in the citric acid cycle. Succinate coenzyme Q reductase forms part of the electron transport chain. Now, it's quite a large protein. It's a heterodimer, which means it's got 2 subunits, one 70 kilodalton and one 27 kilodalton subunit. Now, the larger subunit binds FAD covalently via a histidine residue. So, succinate dehydrogenase is covalently linked to the coenzyme FAD, flavine adenine dinucleotide. This enzyme has 3 different iron sulfur clusters, and its function is to carry out the oxidation of succinate to fumarate. We know that it's carrying out an oxidation reaction because it is covalently bound to FAD, and FAD is can become reduced in that oxidation reaction. So this is the reaction catalyzed by succinate dehydrogenase. Succinate oxidized, and in the process FAD is reduced to FADH2 and fumarate is formed. For the oxidation to happen, these protons are removed and a double bond is formed over there. So there's removal of protons across a carbon-carbon bond to form the double bond, and transfumarate is formed. So in this reaction, an alkane is being oxidized to an alkene, and this oxidation reaction isn't largely favorable, and because of that there's not sufficient energy to reduce NAD+. We do not have enough energy to reduce NAD+, but FAD requires less energy, as you will see when you look at your table of electronic potentials from chapter 3. and so there is sufficient energy to reduce FAD to FADH2 in this oxidation reaction of an alkane to form an alkene. It is a stereospecific reaction. Again, the Pro-S hydrogen is removed from one carbon and the Pro-R hydrogen is removed from the other carbon. So these two carbons, the one hydrogen is the Pro-S one, the other hydrogen is the Pro-R one. Again, from your stereochemistry, you remember what Pro-S and Pro-R means. And of course, the stereospecificity is again indicative of the fact that it is an enzyme catalyzing this reaction. So what happens? These electrons they go from succinate to FAD to form FADH2. Then they go from FADH2 to iron sulfur clusters to coenzyme Q, and that happens in the electron transport chain, as we shall see. And that is how succinate dehydrogenase is linked to the electron transport chain, because it is covalently bound to this FAD, which is going to send electrons directly to the electron transport chain. Okay, next reaction is the fumarase reaction. Fumarase converts fumarate to malate via the addition of water, transaddition of the elements of water across the double bond. So there are the elements of water. It's a hydrogen and an OH. And malate structure is over there. Then the last reaction of the citric acid cycle is the malate dehydrogenase reaction, converting malate to oxaloacetate. Because it's dehydrogenase, we already know oxidation is going to happen and NAD is going to be reduced to form NADH. So it's an oxidation reaction coupled to the reduction of NAD+. This is the fourth coenzyme reduced via oxidation of a single acetate unit. So from one acetate unit, when it enters the citric acid cycle, four reduced coenzymes are going to be produced, 3 NADHs and 1 FADH2. And now we see here that the delta G standard is around positive 30 kilojoules per mole. We saw this already. This reaction is not very spontaneous. It is in fact endergonic on its own, telling us that the concentration of oxaloacetate in the mitochondrion is very low. The reaction, however, can be pulled forward by the highly favorable citrate synthase reaction. Alright, so intermediates serve as a starting point for many biosynthetic processes. So these intermediates, and we've spoken about the citric acid cycle really as being a catabolic process, but the citric acid cycle is actually anabolic because it also serves as a starting point for many biosynthetic processes, building up processes. So many of these citric acid cycle intermediates can then go out of the cycle and go and form, for example, amino acids or nucleotides or things like that from the intermediates of the citric acid cycle. So we can call the citric acid cycle anabolic. Another thing is that there are anaplerotic reactions. Now, anaplerotic reactions are side reactions that feed intermediates back into the cycle. So when we speak about it being anabolic and biosynthetic, we're speaking about the intermediates that are coming out of the cycle and going off to be used to make amino acids or to make nucleotides or fatty acids or whatever it is. Then there are also anaplerotic reactions which feed the intermediates back into the cycle. So, for example, oxaloacetate can come from phosphoenol pyruvate into the cycle that way, and it doesn't only have to be formed through the cycle itself. And this happens via the pyruvate carboxylase enzyme. Alright, so the last final part about the citric acid cycle we need to worry about is regulation of the cycle. Now, the citric acid cycle is very important. It's the link between glycolysis and the electron transport chain and the production of large amounts of energy. So because of that, it needs to be carefully controlled. If we've got too much energy, we need to slow down the cycle. If we've got too little energy, we need to speed up the cycle. So we've already had a look at this, and we've already determined which enzymes we feel would be the sites of regulation by looking at the large negative delta G values. And they, of course, are these three enzymes over here: citrate synthase, isocitrate dehydrogenase, and alpha-ketoglutarate dehydrogenase are our three sites of regulation for the citric acid cycle. And here we can see citrate synthase, isocitrate dehydrogenase, and alpha-ketoglutarate dehydrogenase, and what regulates them. In addition to citrate synthase, isocitrate dehydrogenase, and alpha-ketoglutarate dehydrogenase, the pyruvate dehydrogenase complex, which of course produces acetyl-CoA to feed into the cycle, also is a site of regulation. So the regulatory signals in red are the inhibitors and in green are the promoters. So acetyl-CoA, NADH, and ATP inhibit the citric acid cycle. If we've got too much of any of those, we do not need to produce more energy, whereas NAD and ADP stimulate the citric acid cycle, because if we've got too much of those, it means we require more energy. So there are our enzymes that are the sites of regulation. NADH, we see, inhibits all four enzymes. So if there's a lot of NADH, all four enzymes are going to be inhibited to slow down the process and shut it down. If, on the other hand, there's a high ADP to ATP ratio, a high NAD plus to NADH ratio, it means the cell is low in energy, and that is why those signals cause the cycle to increase. Succinyl-CoA is an intracycle regulator. It particularly regulates alpha-ketoglutarate dehydrogenase and citrate synthase. And of course, it's also going to be an inhibitor, because if there's a lot of succinyl-CoA, it means that the cycle is producing or being produced too rapidly. Too much NAD plus is being formed, and there will be too much energy and it needs to slow down. Pyruvate carboxylase, however, is stimulated by acetyl-CoA. So while acetyl-CoA inhibits pyruvate dehydrogenase, because if there's lots of acetyl-CoA, we don't want more acetyl-CoA to be formed, acetyl-CoA promotes the enzyme activity of pyruvate carboxylase. Now remember, pyruvate carboxylase forms oxaloacetate in an anaplerotic reaction. So when there's lots of acetyl-CoA, we need to produce more oxaloacetate so that oxaloacetate can combine with acetyl-CoA to form citrate. And so acetyl-CoA is an upregulator of pyruvate carboxylase. Right, and that's the end of the citric acid cycle.